Let's cover lecture 2, index notation. And index notation is also known as Euler notation. What is index notation? Index notation allows us to perform complicated mathematical operations in shorthand. It also allows us to derive expressions to be straightforward, in a straightforward manner. Whenever we use a lowercase Latin index, and it does not appear to be repeated, we call that a free index. So, and a Latin index will take values of 1, 2, and 3. The symbolism BI stands for the collection of B1, B2, and B3. In this case, I is a free index, and this corresponds, has a letter I, and so I takes values of 1, 2, and 3. The symbolism AIJ, on the other hand, stands for the collection of A11, A12, A13, A21, A22, A23, A31, A32, and A33. Since I can take values 1 through 3, and J can take values of 1 through 3, then you really have 9 components, and these are the 9 components. In this case, I and J are free indices. Summation convention. Whenever a lowercase Latin index appears repeated once, or basically appears twice, then it is a summation over the index. And so the repeated index is also called a dummy index. And the range also goes from 1 through 3. Here's an example of a summation convention. The symbolism AIJ, BJ, right? In this case, obviously, J is repeated. I is a free index because it's not repeated. So therefore, this here represents a summation over J. And so it stands for 3 sums. I can take values of 1, 2, and 3. So since I is not repeated, we have I of 1, I of 2, and I of 3. So that's what that one is. Now, it's summation over J 1 through 3, and that's why you get A11, B1 plus A12, B2 plus A13, B3. You can see here J is repeated, and that's why that worked out that way for the first equation. The second equation, I is 2, so therefore I have A21B1 plus A22B2 plus A23B3, and then I have A31B1 plus A32B2 plus A33B3. A system of quantities that depends on one index they're also called systems of the first order. So here BI is a system of first order. If a quantity depends on 2 indices, we call those second order. So AIJ has 2 indices, that's a second order system. A single quantity A, for example, with no index, or temperature T, we call that a system of order 0. A system of order 0 has 1 component. A first order system has 3 components. A second order system has 9 components, and a third order system has 27 components. A second order system is symmetric if the components are unaltered when we change the indices in this manner. So AIJ equals AJI. The system is Skewsymmetric if the interchange of indices alters the sign of the component, but not its magnitude. Here, AIJ equals the minus of AJI. We call that Skewsymmetric. So say we have A1 equals 10, A2 equals minus 15, A3 equals 6. So this is an example. B1 is 3, B2 is minus 4, B3 is 1, and then I'm giving values of C1, C2, and C3. I want to calculate AICI B3 and AIBI A2. You can see here clearly that I is repeated. So that must be summation over I. Here I is repeated, and so is summation over I as well. So what do? We do summation over I. B3 is known and B3 is 1. So I can factor B3 1 because I can factor B3, which is 1, and then do the summation over I. And here you can see A1 is 10 and C1 is 16. So that's that plus, and then A2 times C2. And so then I have minus 15 times 12, which is this term, and then A3 times C3, which is this term. And you can see there that I have completed this calculation as minus 38. AI, BI, A2, here I is repeated, and I invite you to pause the video and see if you can get it on your own at this point. But you can see here AI and BI, A2 here has a value of minus 15. I can factor that out, and the I is the one repeated over. So that's 10 times 3 plus minus 15 times 4. So basically multiplying these two here. And then 6 times 1, which is this term. And then I'll add it to get minus 1,440. The expression AI, BI, CJ is a first order system. Why? Because I is repeated and J is a free index. So since I is repeated and J is a free index, that's a first order system. And that will correspond components of a vector potentially. So in this case, I will calculate the scalar AI, BI as, and you can see here the values 10 times 3, and then I have minus 15 times 4, and then 6 times 1. I can do that calculation there. And when I complete the calculation, I get 96. So 96 times the fact that I have a free index J means that those are components of C1, C2, and C3, which are known. They're 16, 12, minus 3. So that's right here, 16, 12, minus 3. So 96 times this vector with those components. Example 3, say I have CJ, BK, CJ, that's a first order system. Why? Because J is repeated, but K is free. So then I will calculate the scalar CJ times CJ, which is really a summation over J. So here I get C11 times C11 plus C22 times C22 plus C33 times C33. So that's 16 squared plus 12 squared plus minus 3 squared, and that's 409. In vector form, that's 409 times, and now since K is a free index, I'll insert B1, B2, and B3, and this is a vector whose components are known here, 3 minus 4, 1. So I know this right here. Example 4, I have this expression, AI, BI, CJ, AK. That's a second order system with free indices J and K. So here, J and K are free indices. I is repeated here, and so it's summation over I. Now I already calculated AI times BI. That calculation came out to be 96 earlier. So then I only have J and K free index, so then I can now put them in a matrix, 96 times C11A1, so that's this term, C1A2, which is this term, and so forth. I'll just put it in matrix format with the 96 times whatever these terms are. So again, this term here is AIBI is 96. I calculated that earlier. And then this term here is C1A1. So I know C1 and A1 from what was given to us here. C1 is 16 and A1 is 10. So that's 160. And times 96, you will get this term. Given the values of this, and so I have a bunch of values given to us, and this is a first order system because it has one index. These B's are a second order system because it has two indices. And C is a first order system because it has one index. The question here is to compute or denote the array for the following: AI, B2I. So I want to calculate this. Now I is summation over, I is repeated, so it's summation over I. And so as a consequence, I can do that. So 2 is fixed. So I have A1, B21 plus, now I is 2. So A2, B22 plus A3, B23, and so forth. So A1 here is 2, B21 is minus 3, A2 is 3, B22 is 1, is all given here at the top. A3 is 4, B23 is minus 1, so I can just calculate this as minus 7. Example 6, we want to calculate this. Well, J is repeated again, so that's similar process. B12, in this case, J is repeated, so J is 1, so B12C1, and then J is 2, B22C2 plus B23 C3. And then you can then plug in the values from up here, and you get minus 19. Problem 7. I have this expression. It's a second order system. Why? Because ing are free indices, and this is a specified value of B22. I know B22. One way to write this array with an I as a row index and j as a column index, you could do it the other way around, is the following. So let's look. So B22 is known, and B22 here is 1. And then so this term here is A1C1. So it's going to be a 3 by 3 because ing are free indices. And here then I have A1C1, and I know A1, which is 2, and C1 is 1. So clearly that's 2. And then I go to A1C3. A1C3. So A1 times, I'll say, okay, so this term here is A1C2, I'm sorry, A1C2. So I have A1, which is 2, and C2 is 3. So that's 6. 2 times 3 is 6. Okay, so that's what I got. And B22 is 1, so that's why that's 6. And so you can then populate the rest of it. So comments. The subscript used for the dummy index is immaterial. I can just make it I can make it J, I can make it K. It doesn't matter because if I sum over J or sum over K or sum over I, it doesn't matter, I get the same answer. Dummy indices appear more than twice has no meaning. So if you were to have AI, BII, that's not recommended. It has no meaning in index notation. Kronecker delta ij is 1 if ing are equal, 0 if ing are not equal. And notice how ing are free indices. And so in this case, since ing are free indices, then this will be a 3 by 3 and a second order system. Let's consider the expression of aij del jk. For those terms in the summation where j is not equal to k, so anytime j is not equal to k, those terms will be 0. And so only when j equals k, we get a non-zero contribution. And for that term, the Kronecker delta is unity. So therefore, if I were to have this, all you have to do is cancel j and bring k over. And so you get aik. Now notice that this is a second order system because j is repeated, but I and k are free indices. And so here I've canceled j, brought k over, and I get aik. You could also have this situation. You could have aij delta del ik. So anytime you have this is a different example altogether, not here. Cancel I, bring k over, and you get akj. Note that del kk is 3. Why? Because k is repeated in this case, and so that will be equal to del 1, 1 plus del 2, 2 plus del 3, 3. And that will be equal to 3. Permutation symbol. The third order system epsilon ijk is completely skew symmetric. It is also called alternating tensor, and its components are altered in sign but not in absolute value when any two indices are interchanged. So the components have the values like this. So epsilon ijk equals 0 if any two indices are the same. If ijk is an even permutation of 1, 2, and 3, then the value is 1. If ijk is an odd permutation of 1, and 2, and 3, then I get minus 1. And what that looks like is this. So if I have epsilon 1, 2, 3, that's 1. If I have epsilon 1, 3, 2, that's minus 1. And then if I have epsilon 2, 1, 3, that's minus 1, and so forth. So that concludes the short lecture in index notation.
Well, what I want to do is now derive all these, but by hand. Let's do that.
Okay, let's start with index notation, lecture number 0. And so we're going to cover index notation. And so what I want to say is that whenever we use a lowercase Latin index and it does not appear to be repeated, it is a free index and takes values I equals 1, 2, and 3. As an example, I want to show you that. The symbolism BI stands for B1, for example, B2, B3. Okay, so in this example, here, I took values 1, 2, and 3. BI stands for B1, B2, and B3. Anytime you see symbolisms of AIJ, that stands for A11, A22, A33, A13, and so forth. Does that make sense? Does that make sense?
Yeah.
Yeah.
So whenever we use a Greek letter and we use a free index, that's going to be, by convention, that's going to be an index that takes only values of 1 and 2. So a Greek letter, so if I were to have a Greek letter and I have B alpha in this case, then B alpha in this case only takes values such that alpha can be B1 and B2. So again, BI stands for B1, B2, and B3. AIJ stands for A11, A22, A33, and A13. And then if it's a Greek symbol, it only takes values of 1 and 2. Whenever the index appears repeated once, and that just means that it appears twice, then the summation over that index is implied. What do I mean with that? So what I mean with that is that if I now take AIJ, BJ, I want to show you something. Can you notice here that J is repeated? Do you see that J is repeated? Well, all that means, and I is a free index, all that means is I have summation over J. J equals 1 through 3. And I call this Euler notation. I do that so it's quicker for me to run through all the calculations. Otherwise, it will take forever to do. And because I is a free index, then that means that this is true from J equals 1 to 3, so J sum over J, but also I is a free index. And so that's, this equation is true for I equals 1, 2, and 3. So there's really 3 equations here. And you can see here that I have this right here. This right here is A11, A12, and A13. So this right here is equal to the A matrix times the B vector. So I have the A matrix times B. And so this multiplication, you can see here, if for value of I equals 1, for value of I equals 1, this I is 1, J takes values 1 through 3. So that's summation over J. So therefore, that's equal to A11 times B1 plus A12 times B2 plus A13 times B3. That's your first equation. That's for I equals 1. And then for I equals 2, and then for I equals 3. So hopefully that's clear. And so what I want to cover now is, not sure what's going on. Yeah, you can see it expanded here. So if I have a system of quantities, and let's give you an example. So I have a system of quantities and I have no indices. No indices are shown. That's a zeroth order tensor. If I have a 0 indices, I only have one component and the scatter is phi in this example. A good example of a scatter is temperature. In this case, phi could be a potential. If I have one index, we call that a first order tensor, and there'll be 3 components there. And that'll be a vector vi that has 3 components, that vector. If I have 2 indices, that'll be a second order tensor, and that'll be 9 components. And then I'll call that a second order tensor, Aij. So again, here I have 2 indices, and here I have 1 index. Here I have a scalar quantity. So you can see here very clearly that those correspond to whether you have an index or 1 index or 2 indices. And that also tells you about the system order and how many components you have. So a symmetric and skew-symmetric tensor let's discuss that. I have a definition of a second order system. A second order system is symmetric if the components are unaltered when the indices are unchanged. So say I take AGI, that's equal to AIJ. In that case, if I have that, then that is a symmetric tensor if I have this situation. The system is skew symmetric if I interchange the indices, but the signs get changed. As an example, if I take AJI and I make this the equal of negative AIJ, this is a skew symmetric tensor. I hope that makes sense. And so now let's look at this derivatives. And when we talk about derivatives, partial derivatives, we may use the symbolism called this parenthesis comma j. And that's going to be equal to the partial of something relative to xj. That's what that means. It's a way of simplifying expressions so that we can move very quickly through the derivations. Index notation is really used to simplify notation. That's really what it's used for. So let's consider this example. Here, I have a force vector Fi and the stiffness matrix here. And then here on the right-hand side, I have a vector. Well, how many free indices I have? So I really have one free index because I shows up in the left side, I shows up in the right side, so I take values of 1 through 3, while j is repeated in the same term. If j is repeated, that's summation over j. So as a consequence, what I really have here when expanded is this. I have k11, k12, k13, and I have u1, u2, and u3. And if I multiply this row times this column, then I'll get the force F1. So that's what that one is about. And there are 3 equations here, and we've expanded it. So there are also special symbols that we use in solid mechanics. There's something called the Kronecker delta. The Kronecker delta takes values of 1 if I equals j. If I is not equal to j, then this takes value of 0. That in turns out that this becomes the components of an identity matrix. So the permutation symbol ijk is completely skew symmetric, and that's another one that we're going to be using. And it is a third order system because it has three indices, as you can see here, I, J, and K. And so if any of these indices are repeated, then epsilon ijk is 0. And if and I will show you how to do this. So the way I like doing this is if I write 1, 2, and 3, and all my indices here, say I have 1, 2, and 3 as indices, epsilon 1, 2, 3, then epsilon 1, 2, 3 will become 1. If I have instead 3, 2, 1, then I'm going to have this to be a value of -1. So if I have this order in any way, this is going to be 1. If I have this order in this way, then I'm going to have this to be equal -1. And again, there's 3 indices here. So there's really 3 times 3 times 3, 27 components of epsilon, but only 6 are non-zero. And they're going to be these ones here. You can see them here. Because they follow this rule here, as you can see. Okay, so and feel free to pause the video and maybe even derive this on yourself if you want to. Examples for this, we can go through a number of examples. So here I have an example of the trace. So del kk, k is repeated, is that correct? K is repeated? Well, it's repeated, so it's summation over k, right? Since it's summation over k, then I have del 1, 1 plus del 2, 2 plus del 3, 3. But del 1, 1 is 1 because I equals j, so that's 1. 2, 2, that's repeated, so that's 1. And then 3, 3 is repeated, and so that's 1. So I get a value of 3. That is a trace of del ij. If I have aj, bjk, in this example, j is repeated, and I and k are free indices. That tells me I really have a second order tensor. So you can see that here, because look, j is repeated in the same term. So that means that this is summation over j from 1 through 3. Just imagine a summation symbol right in front from j equals 1 to 3. And you can see here clearly that I and k are free indices, completely free. That tells me that since I have two free indices, that is a second order tensor. And I'm calling it CIK. And it's summation over j. And so as a consequence, you can see here that I have expanded it very simply. You can see that here expanded very nicely. And you can see the components there, A1J, BJ1, A1J, BJ2, A1J, BJ3, and so forth, okay? And each of these can be expanded further, right? Because J is repeated. So this component right here can be expanded as A11, B11, plus A12 times B21, plus A13 times B31. So that will be three components here. And I will have 3 and 3 and 3 and so forth. So that's how you do that. And why is it a second order tensor? You can see here clearly that is a 3 by 3 because there's two indices that are independent and they're not repeated and they're free. Here I have another example, and I want to show you something cool here. Aij equals del j times del jk, sorry about that, Aij times del jk, and you can see here j is repeated, and del is a canonical symbol delta, so j is repeated, and I have aik, that's going to be equal to aik, and you can do it yourself at home so you can check that. You can see it's going to work out really nicely. Why? You can expand it. I and k are free indices, j is repeated, and so you can expand this, and what you'll find is that you'll get aik. And in the future, if you don't want to expand it, all you have to do anytime you have anything multiplied by delta, just cancel j and bring the k over, and then that will simplify it very nicely. I want to also talk about here aij del ij. This is an interesting one because in this case ij and ij are repeated, so that's double summation over I and over j. So this is a scalar quantity. There's no free indices here. It's completely scalar because I and j are repeated. Well, here above you can see that I and k are free, so that's a second order tensor to start with. So if I were to expand that, I can do it very quickly. You can see that here. I have some double summation over I and j. And you can see here that when I expand this, I get A11 del 11 plus A12 del 12 plus A13 del 13 plus A23 del 23 plus blah. And you can continue on. And so you can see here now that del 11 is 1 because that's canonical delta. Anytime I equals j, that takes value of 1. And so this goes. Del 12 is 0 because I is different from j. And so this goes away. This is 1. This is 0. That's 0. That's 0. That's 1. And that's 0. And you can see that here. This cancels out. And what I get here is the trace of A. Again, let's evaluate derivative of x comma xi comma j. So let's look at that carefully. So xi comma j. If you remember, I told you that comma j means derivative of something with respect to xj. And so here I and j are free indices, and that's a comma right here. Therefore, I and j are free indices, therefore, that's a second order tensor. And so I can write that in this manner. You can see that here. I can write it in this manner. And so derivative of x1 respect to x1. These are the components. These are the components. xi comma j are the components of this second order tensor, this matrix, this 3 by 3 matrix. You can see here very clearly that this derivative, if x1 and 2 and 3 are independent components, that this derivative here becomes 1. And this is 0, and that's 0. That's 0, that's 1, that's 0. That's 0, that's 0, that's 1. And so that'll be basically your Kronecker delta. You can see that here. You can see here that this right here, xi comma j, becomes your Kronecker delta. So that's del ij, as you can see there. Let's consider now this example. Say I have fi equals xij, uj to the exponent n. So I want to find out what is this derivative. What is derivative of fi respect to derivative of uj? That's not very hard. I'll take the derivative of this first, right? And then times ui to uj to the n plus the derivative of this term times that. And so then I'll go through that. So let's take the derivative of this term respect to uj. So when I do that, has no uj. Let's say it's a linear system. We can make it nonlinear just for fun, but I'm not making it nonlinear right now. Although this is actually nonlinear if you look at it, because of this to the exponent n. But k can also depend on u. K can depend on the stiffness or on the deflection u. In this example, I'll take the derivative of fi respect to um. That's what I want to do. Now you will say, well, that doesn't make sense because there's no um here. But I can do that, and I encourage you to do that. Anytime you take a derivative respect to a variable, make sure you use an index that was not used in the right-hand side so you don't get confused. Here, I used an index that was not used in the right-hand side to take that derivative. Here, I did ask you to take the derivative of fi respect to uj, but you can change it to um if you want. It's a dumb index. All I'm asking you to do is to find this derivative. I don't care how you do that. So once you take this derivative, what you find is that I have kij here, n drops here in the front end, and then I have uj, so to the n to the minus 1, so that's it, right? Then I have the chain rule. I have the derivative of uj respect to um. I have to continue that chain rule throughout. Now, guess what? I just showed you that there's a Kronecker delta just above right here in the above example. So as a consequence, this becomes del jm. Now I have to still continue expanding. I can continue expanding. There should be an equal sign here in the front. I'll correct it. But now notice how j is repeated here, right? This is del jm. J is repeated here, so I can cancel j and bring m over, like I discussed earlier. And so when I do that, I'll find that this is what I get. Now there should be an equal here, which will be fixed at the moment. Okay, so I can continue now. So this is a second order tensor because m and I are on both sides of the equation. Now consider another example. Let's say I have the strain energy of a system. This is going to come up a lot. Say I have a situation where I have the energy of a spring, 1/2 times Fr UR. R is repeated, is that correct? Since R is repeated, is summation in front of the R. Is summation in front of the R, and as a consequence, this is a scalar quantity. Energy is a scalar quantity. And Fr are the components of the force. So Fr is Krj times Uj. Now, R is in the left side and also in the right-hand side. So that's a free index. J is repeated. And since J is repeated, that's summation over J. Okay? So this, again, is a first order tensor because R is the only free index and R can take values of 1 through 3. Here, however, is scalar quantity because R is repeated. If I substitute what Fr is into this equation, what I get is Krj times Uj times Ur. And you can see here what I've done is I've substituted this expression in here. And so now that's the strain energy of a three-dimensional spring. Okay, and that's a zeroth order tensor because now you can see that R is repeated, J is repeated. Now we want to find, in this example, what is the derivative of U respect to UN. I'm just interested in finding that derivative. So what is that? Well, N is a free index, so that now becomes a component of a vector. So derivative e respect to u1, derivative u2 respect to derivative e respect to u2, derivative e respect to u3. So those are the three components now. So I have 1/2 krj. So now you can see here the derivative with respect to un. I have to now take derivatives. There is a multiplication here. So you can see here I take the derivative of this with respect to un times the rest of it, and that's here, plus 1/2 krj uj, and then I'll now take the derivative ur with respect to un. Now we already know this Kronecker delta, and that's Kronecker delta. So I'll go then jump here. Then I have u del jn. That's del jn, as I showed you earlier. Del jn. And this right here is del jr. I hope you're following with me so far. And so now I can then take this j, cancel it out, and bring n over. I'll take here, these r, cancel it out, and bring n over. And when I do that, it simplifies very nicely, because you can see here the j cancels out, the n comes over, so I get rn ur, and then here you can see here very nicely cancels out the r, and then n comes over, so I get 1/2 krn ur plus 1/2 knj uj. Now you'll be confused now. You'll say, well, I have different indices now, but not really. If you notice, r is repeated here and j is repeated, so these are dummy indices, right? Dummy indices means that j can, it could be j, it could be k, whatever, is repeated. It's repeated, so therefore a summation over j equals 1 through 3. Here is summation over r equals 1 through 3. It doesn't matter now, right? So therefore I can interchange r with j if I wanted to, and then combine the terms because it's the same thing. You can also expand it one by one, but that takes too long. So why not just take that and make it combine? You could also do it, another way to do this, combining them will give you the same answer, just adding them up. Just make these r or j, and then just add them up, and then this 1/2 cancels. Or you can do a trick that people sometimes do. You can do a factorization. If you factor out from these variables, us, just make it up, a variable, us. Factor it out, and when you factor it out, you get krn, and since I factored out a ur, I must have del rs, because us times del rs, s cancels out, so r comes over, and that becomes that term. Plus, if I factor out us out of uj, I get del js, and you can see here us times del js. There you go. S cancels out, j comes over, and that becomes that exact same thing. So I'm able to factor out, and that's another way that people do these calculations sometimes. Then you can notice here that r is repeated, you can bring the s over. J is repeated, you can bring the s over. And when you do that, it naturally becomes the same value. They just become kns plus kns, and then it just becomes that, which is exactly what I told you you're going to get earlier. So let's look at a new example. Let's say I have bij equals alpha aij plus beta cij, where aij and cij are linearly independent variables. So say I have this example here. Sometimes you could have this situation where you want to find the derivative of bij respect to akm. So I ask you to find this derivative. One approach that people use is you have alpha times the derivative of aij respect to akm plus beta derivative of cij respect to akm. And you can see that here. Now, cij does not depend on a, so that's 0. And then in this case, I have the situation where this could become Kronecker delta. So that's del ik, del jm. Because this can only be 1 if I equals k and j equals m. That's the only way. And this can only happen if this derivative looks like this. Okay? So that's something to keep in mind as you work through different problems. So this is a fourth order tensor, has 4 indices, and they're all free. And you're going to see that in this course. And in your homework 0, you're going to see 4 fourth order tensors. So later in class, we'll show that the strain energy of an elastic body, and I'll show you that, can be represented as follows. I'll show you that pi equals 1/2 the stress tensor times ui comma j. And here, I is repeated, j is repeated, and you can see here the scalar quantity because this is totally repeated. So that's double summation of I through 3 and j 1 through 3. So therefore, you will see that um, I can write this as follows. I can do a little trick that I'm going to do in class later. So please memorize how I'm doing this, but we're going to do this in class later. So uij, ui comma j can be written this manner. 1/2 ui comma j plus uj comma I plus 1/2 ui comma j minus uj comma I. And look at this. This is the same as that because this term right here cancels out with that term. And 1/2 plus 1/2 is 1. So therefore, clearly, that cancels out, and you get that. So that's the same thing. Just memorize that. We're going to look at that later. Now, this is going to be called strain later. We're going to show you that. This is called the rotation tensor, and it's a skew-symmetric tensor. So, for example, if I were to look at omega ij, and I were to do a expansion. So if I do omega ij, right, and I wrote 1/2 ui comma j minus uj comma I, and I switched it out. I switched j and I. Just switch it out just for fun. You will see that when I switch it out, this definition becomes the minus of that. So I can just then say that pi equals 1/2 sigma ij times epsilon ij plus 1/2 sigma ij derivative of omega ij. Later, I'm going to show you the sigma ij symmetric. And what I want to show you here is when you have a symmetric tensor times a skew symmetric tensor, when I have this situation here, you're going to find that this will be equal to 0. And I'll have you prove that. The way to prove that people use is sigma j equals sigma ji, so it's symmetric. Omega j equals minus omega ji. I just showed you that for what skew symmetric means, and also showed you the rotation sensor is skew symmetric. And if I'm going to fast pause the video and check it out, so let sigma j omega ij be equal to z, just for fun, see what happens. And guess what happens? When I do that, I know that sigma j is sigma ji, so I can just substitute that, right? So if I switch it out, I have sigma j ji times omega ji equals c. Since j and I are dummy indices, I and j are dummy indices, so I can just do whatever. I can just switch it out just for fun if I wanted to. Well, guess what? Sigma ji is equal to sigma ij, so that's the same, right? So that's sigma ij. But this is minus omega ij. So therefore, c has to be equal to 0, because if I add these two, if I add them linearly, you're going to get, I add 1 and 2, so sigma j times omega j is c, sigma j times minus omega j equals c. If I add this up, 2c equals 0, and c becomes 0.